This is Advanced Functions Lesson 5.2, Exploring Quotients of Polynomial Functions. We already have talked about a reciprocal function. That's when you take any polynomial function, like say quadratic, and you just flip it, you reciprocate it. That becomes 1 over. That's a reciprocal function. A rational function, so we get these two words mixed up sometimes, but a rational function means that generally you've got a polynomial in the numerator and a polynomial in the denominator. And of course our denominators cannot equal 0. And when they do, we have asymptotes. Vertical asymptotes cannot be crossed, but horizontal asymptotes can be crossed, and we do see this happen. Really, the horizontal asymptotes help us to define end behavior. That's what they're used for specifically. Let's do an example. So here's a graph. Here's the equation of that graph. And we're going to list a bunch of key characteristics. So first we take the equation, we're going to factor and simplify or use long division if that's what's required here. So our first step here is we will factor because our numerator will factor. So we're going to, that's a difference of squares in the numerator. Let's rewrite that as x minus 1 times x plus 1 over x minus 1. So there's your first step, is to factor. Now, when we take a look at that equation, we see there is a restriction that x cannot equal 1 on the denominator. X cannot equal 1, but look at the graph. At the graph, what's happening when x is 1? When x is 1, we have a hole in our line. This just looks like a straight line, but it's got a hole in it. And there's a hole because x cannot equal 1. So let's get some more detail on that. The next step I want to look at with this equation is that I have two factors that match, x minus 1 and x minus 1. Those binomials match exactly, so I can cancel them out. So I'm going to cancel these out here. That leaves me with just x plus 1. So if I asked you to graph x plus 1, you'd be graphing a line, this red line that you see here on the left. So after we've simplified the equation, we have a little, what looks like a linear equation, a linear function, y equals x plus 1. That's this line. But x cannot equal 1. So we have a hole there. A hole occurs when a factor that was a restriction cancels out in the denominator. So I'm going to write that over there under the key characteristics. Is we have a hole. We have a hole at x equals 1 since that factor canceled out. That's how you get a hole in a graph when your restriction factor in the denominator cancels out. Another characteristic when we look at the graph is that it looks linear. And that's because our equation simplified to y equals x plus 1, but we still had the restriction that x could not equal 1. So what else can we see on the graph? Something important is usually the x-intercept. So here's my x-intercept here. I just put a green dot on it. We have an x-intercept. We get the x-intercepts from the zeros of the numerator that are left behind. So this factor was left behind. So this tells me that when x equals -1, I'm going to have an x-intercept. So we have an x-intercept at x equals -1. And again, that came from the numerator. That's where we get the zeros from. Another key characteristic we usually talk about is the y-intercept. And the y-intercept in this case is, put another green dot there, the y-intercept is 0, 1, and we can get that by subbing into the original function f at 0. Sub in f at 0 into the original question, and you're going to get -1 over -1, which is 1. So we've got two more examples here. We're going to take a look at this first graph here, and this is the equation that matches it. Now we can't do any factoring, we can't do any canceling or simplifying or anything like that here. It's as simple as it's going to get. So what can we tell? What characteristics can we tell by looking at the equation or by looking at the graph? First of all, we have a restriction on the denominator. The restriction on the denominator is that x cannot equal -1. And since that restriction didn't cancel out, we have a vertical asymptote there. So there's our first key characteristic is we have I'll put VA, short for vertical asymptote, at x equals -1. And that comes from the denominator. What else have we got? Have we got a horizontal asymptote? It looks like it. It's not visible clearly on the graph, but there is a horizontal asymptote. A horizontal asymptote can only occur when the degree of the numerator, in this case our degree of the numerator is 0, because this is really actually the power of 0 to be technical, right? That's what you have there. So the degree of the numerator is less than the degree of the denominator. So that's when we get a horizontal asymptote. We're going to talk a lot more about that later. But when your degree of the numerator is less than the degree of the denominator, you're going to get a horizontal asymptote. So we have a horizontal asymptote. And in this case, it's right along the x-axis. Right along here, we have a horizontal asymptote. So let me write that in there. So again, we have the horizontal asymptote right across here. This function can never equal 0. There's nothing you can sub in for x that is going to turn this equal to 0. So we have a horizontal asymptote there. And now just to bring in some vocabulary from earlier in the course, this is a discontinuous function, because if I were drawing this with my pencil, I would have to lift it up to get over here. I'd have to jump over the vertical asymptote. So this is a discontinuous function. All right, so we've got the vertical asymptote, the horizontal asymptote. Sorry, that was my phone. The next, so we've got vertical, horizontal asymptote. The next thing we'll look at is zeros, x-intercepts. So you can look at the graph and see there aren't any x-intercepts. We've got a horizontal asymptote. That doesn't mean there wouldn't be any x-intercepts, but the horizontal asymptote defines our end behavior. So if we look at the ends, it's not going to cross the horizontal asymptotes. You're not going to get any zeros. If you didn't have a graph and you just had the equation, the way you would tell if you had a horizontal, the way you tell you have zeros from the horizontal asymptote is from the numerator. So I'm not going to have any zeros because I don't have, algebraically, I can't get a value of 0. We already talked about that. So there's no x-intercepts, or no zeros, or no roots. We can also talk about the y-intercept. That's a key characteristic. Y-intercept is here on the graph. If I can't really tell what that is, I would substitute in to find it. F at 0 is going to be 3 over 0 plus 1. So my y-intercept is 0, 3. And I think those are all the main characteristics we have here. So we've already listed all those because there's not much we could do with the equation. So that's a pretty straightforward look at the graph. Looks like the parent function we have for the reciprocal function, and that's really all it is. It's the parent function with an a value of 3. So it's got a bit of a stretch, and it's been shifted 1 unit to the left. That's why our asymptote is over 1 unit to the left. Okay, next one. Next one also looks kind of similar to the one above it, but the equation is very different. So we can get a lot of information out of this equation. Remember, the first thing we want to do is factor. So we can factor this denominator. The numerator is already linear, so I'm going to leave that x plus 1. The denominator is an easy trinomial. It factors to x minus 3 and x plus 1. Okay, so restrictions. X cannot equal 3 or -1. And what does that mean about the graph? Well, it means two things. So this is a good example. It shows you both. We have let me write it down under the key characteristics. We have a vertical asymptote. Look at the graph. You can see the vertical asymptote at x equals 3. But why don't we have a vertical asymptote at x equals -1? Because that's a restriction too. So think back to the first example we did. So why do we not have a vertical asymptote down here? We have something else happening when x is -1. We have a hole. So do you remember why the hole is? It's because these binomials match exactly. These factors, we cancel them out. That leaves us with a hole. So we have a hole at x equals -1. So that's information that we're getting from the denominator. Let me just put that here. This one gives us a vertical asymptote. This one gives us the hole. So finishing to simplify that equation, once I'm done canceling, I have 1 over x minus 3. But remember, we still have the restriction x cannot equal 3 and x cannot equal -1. Sorry, let's put those in order, low to high. -1 comes first and then 3. What else? What other characteristics have we got here? So we know that the degree of the numerator, and this will be I'll write this out for you in detail later, but the degree of the numerator is a 1. The degree of the denominator is a 2. So since the degree of the numerator is less than the degree of the denominator, we're going to have a horizontal asymptote. And you can see from the graph where that is. So our function will never reach 0. So we have a horizontal asymptote at y equals 0. And the other one we talk about a lot is the y-intercept. So our y-intercept is another key characteristic. We sub in 0 into the function, and when you do all that, you will end up with 0 plus 1 over 0 minus 3. So our y-intercept is going to be at 0, -1/3. So those are all the key characteristics we can get from the equation or from the graph. Another example here, here's the graph and the equation to go with it. The equation we cannot factor, there's nothing that factors, so we can't really simplify. Do not cancel out those x's. They are parts of a binomial. You can't just cancel them. We do have a restriction. X cannot equal -2, so that gives us our first key characteristic, which is we have a vertical asymptote at x equals -2. Now, what does the numerator tell us? The numerator can tell us the x-intercept. So if I solve that little numerator piece, which is an x plus 1, let that equal 0, bring the 1 over, I get x equals -1. So look over at the graph when x is -1, and we have our x-intercept there. We have an x-intercept at -1, 0. So while we're on the topic of intercepts, let's do the y-intercept. The y-intercept, that's when we sub in 0 for x, and we get 1/2. So we have a y-intercept of 0, 1/2. Notice there's no holes in the graph, and there's no holes because nothing canceled. So no holes, because nothing canceled. That's why we have no holes. Nothing cancels. Okay, let's talk about the horizontal asymptote. So this is the first one we've done today where the horizontal asymptote is not along the x-axis. It is at 1. So how could we possibly figure that out? Horizontal asymptotes. We're going to talk about degrees again. If you were to sub in horizontal asymptotes, think of n behavior. So if you were to sub in a really gigantic number in for x, like 1,000,000, you would have 1,000,001, right? Over 1,000,002. That's basically 1. sub in any number you want, a giant number that you want for x. And this 1 and 2 are insignificant if you're adding 1 or adding 2. It's really what you're looking at is the x over the x. So you sub in 10 billion over 10 billion, that gives you a 1. That's where this 1 is coming from. More specifically, when we have an equal degree here, this is an x and this is an x, it means they both kind of have an equal pull on the value of the function. So if I sub in 10 billion here and 10 billion here, they kind of cancel each other out. So when our degrees are equal to each other, you're not always going to get a 1, but you're going to have, I'll show you this now. When the degrees of the numerator and the denominator are the same, then the horizontal asymptote is found by dividing the leading terms, the leading coefficients. So the horizontal asymptote is numerator's leading coefficient divided by denominator's leading coefficient. And in this case, that is simply, write it down here, our horizontal asymptote is found because our degrees are the same, so we call the numerator p at x, that's from our definition. The denominator is called q at x. So when the degree of p at x equals the degree of q at x, we divide leading coefficient, which is, this is a 1 for my numerator, over leading coefficient, that's another 1. So I get a horizontal asymptote at 1 when the degrees are equal, and that's because they have equal strength or power when we sub in numbers here. So I'll add that under the key characteristics. We have a horizontal asymptote at y equals 1. And we did the y-intercept, and I think we covered everything else there. So let's try another one where the horizontal asymptote is in a different place. Here's the equation. So what can we tell about the equation? So let's talk about the one we were just talking about, which is the horizontal asymptote. Let's start with that key characteristic. Oh, sorry, well, we've got to factor first. Let's factor first. We can do some factoring here. The numerator has a greatest common factor of 2. X minus 2, sorry. X minus 2 over, nothing factors here, 3x minus 5. We have restrictions on our denominator. X cannot equal 5/3. So we're going to have, let's put that one up there, we're going to have a vertical asymptote at x equals 5/3. And you can see that drawn. It's very hard to see the scale on the bottom there, but that's 1 2/3 is where the vertical asymptote is. So going back to the horizontal asymptote, let me go back to purple for that, just to keep it all straight. The horizontal asymptote, so our degrees are the same. So we have our p at x degree is 1. Q at x degree is also a 1. So I'll put little 1s there. Those degrees are 1. So we divide the leading coefficient. So what we're going to do is take the leading coefficient. This is degree I'm talking about here, not leading coefficient, degree. The leading coefficient is a 2 in the numerator, and the denominator is a 3. So that means we're going to have a horizontal asymptote. Horizontal asymptote at y equals 2/3, and that's because our degrees, I'm going to circle it here, the degrees of the numerator and the denominator are the same. So that's how we get the horizontal asymptote. What else? We've got no holes, nothing cancels, so we have no holes. What about an x-intercept? So we have an x-intercept. We look at the numerator. This factor right here will tell me that the x-intercept is at 2. X-intercept at 2, 0. And y-intercept. So we calculate that by, once again, subbing in 0. And we get sub in a 0 to the numerator and the denominator, we get -4 or -5, so we're just going to put 4 bits. I think we've covered all of our critical pieces there. Okay, hold on to your hats. This is getting even more complex looking here with our next one. We have an oblique asymptote. That's not vertical or horizontal, but it's slanted. If the degree of the numerator is exactly 1 more than the degree of the denominator, then the equation will have, the function will have a slant asymptote, and we will divide to find that. So look at this graph here. Here we've got this brand new thing, which is an oblique asymptote or a slant asymptote. And that occurs when we get an equation where the degree of the numerator, which in this case is a 2, is 1 more than the degree of the denominator, which is this degree is a 1. So that's how you know you're going to get a slant asymptote. Now, how to figure out where to put that slant asymptote? So let's go through our steps here as usual. We're going to start off with factoring or simplifying if we can. So we can take a greatest common factor of x of the numerator. X plus 2 is left. Denominator, we can't do anything with that. So factor, state restrictions. The next the restriction is x cannot equal -1. And since that restriction did not cancel, it means we're going to have a vertical asymptote at x equals -1, and you can see that on the graph. Okay, going back to our equation, nothing cancels. Don't start canceling those x's out. The first x that you see here is a monomial. You can only cancel that with a single x, and this is not a single x. These two go together as a binomial. And binomials have to match exactly for you to cancel them. This is an x plus 2, this is an x plus 1. They don't match exactly, so nothing cancels. So what else can we tell here? Well, let's look at the numerator. We factored that one out. The numerator, from the numerator, we can get the zeros. So this one gives me x equals 0. If you look at the graph, I'll put a dot there. There's a 0. The second factor gives me a 0 at x equals -2, and that's over here on the graph, put a green dot there. So we have x-intercepts at -2, 0, and we have another one at 0, 0. And whenever you have an x-intercept at 0, 0, that means it's also a y-intercept because it's intersecting both axes at the origin. What else can we tell? So we've got a vertical asymptote, we've got the x-intercepts. Well, since we're doing intercepts, let's do the y-intercept here. I just talked about it, but if you don't remember what I just said, then we sub in to find the y-intercept. That's going to give us 0 plus 0 over 1, which is 0. So the y-intercept is the same. When you have the origin as an x-intercept, then it's also the y-intercept. So the y-intercept and the x-intercept are the same. What else have we got here? Okay, we've got any holes? Oh, no holes, nothing canceled. No holes. So let's talk about that new piece, the oblique asymptote. We've got the degree of the numerator, which in our case is a 2. It's exactly 1 more than the degree of the denominator, which in our case is a 1. So we're going to have an oblique or a slant asymptote. Think of, if you know physically where your obliques are, your obliques where they are in your kind of midsection there, they're slanted. So oblique asymptote, so how we find it, it's the quotient. So we're going to have to do some dividing here to find the equation of this dotted line. For when we have to graph this ourselves, we have to figure out where to put it. So let's get the equation. Let me go to purple here. To find the equation, I'm dividing. So I don't want to take too much space here. Let me move over. Okay, put it underneath the equation. So we've got x plus 1. We're dividing that. So I'm just going to the original question right up here. We're dividing. We're taking x squared plus 2x, and we're dividing that by x plus 1. So I've got, let me clean that up. Okay, so remember, I'm choosing to do long division here because it's my favorite. I need a constant, so I'm going to have to put in a 0 placeholder right here. Now I'll just change colors to help you see the division. I first divide my first term into my first term. That gives me x. I multiply it back down into both parts of the binomial. X squared plus x, and subtract the whole thing. These are gone. 2x minus x is not 2. 2x minus x is x. That's the end of the first step. For the second step, I bring down the 0. Do the division again. First term into the first term. X into x goes once. Multiply it back down. X plus 1. Subtract. We get a remainder of -1, and that's okay. We're going to talk about that later, but the remainder really tells us that x plus 1 is not a factor. This piece over here, right? This is not a factor. We knew that because when we divided right up here at the beginning, when we factored, we would have canceled it out. If it was a factor, then it would have canceled out with something up here, and it didn't. So we already know that about it. Just erase some of this mess that I made. So we know that it's not a factor. And the remainder is what keeps the rational function from reaching the asymptote. So it doesn't matter if that's a -1 or positive 55 million, which it wouldn't be, but don't worry about the remainder. There will be a remainder there. You need to expect there to be a remainder there. What is important is the first top, what we got for our quotient. This is our quotient right here. And look back up to the definition. The equation of the slant or oblique asymptote is the quotient. So that means, back over here to our key characteristics, we've got an oblique asymptote at, now we have to put a y equals, this is an equation, y equals mx plus b, back to grade 9, at y equals x plus 1. That is the equation of this line right here, y equals x plus 1. So you know how to graph that on your own. If not, you're going to have to review that, but that is how you find the equation of where to place the oblique asymptote. So I think we've done all the characteristics there. We're going to go on to do another example. Next one, we've got very weird looking graphs here with no asymptotes drawn in. So we're going to do a little bit more work ourselves now. Still, we're starting with the first equation we want to factor if we can. So can we factor anything here? Look at that numerator. That numerator looks tempting like it might factor, but it's not a difference of squares because that's a plus sign, so we can't do any factoring there. And same with the denominator, it's linear, we can't do any factoring there. So let's look at the restrictions. X cannot equal 2. So there's our first key characteristic, is we have a vertical asymptote at x equals 2, and nothing canceled, so there's no holes. So let's look at the degrees. So we want to look at, so we did the vertical asymptote, now we want to talk about, it's either horizontal or oblique. It's going to be one or the other. It's not, you're not going to have both. So let's talk about our degrees. The degree of the degree of the numerator is 2. The degree of the denominator is 1. So here's degree of the numerator is 2, degree of the denominator is 1. So remember from our last example, our last slide, when the degree of the numerator is greater than the degree of the denominator by 1, we're going to have an oblique asymptote. So we need to divide. So it's going to be, so degree, let me write that here, degree of p at x, that's a numerator, is greater than the degree of q at x by 1. If it was greater than by, if it was greater is by 2, then your asymptote would not be a line, it would be a parabola. If it was greater by 3, it would be cubic, which is really kind of cool, but we don't have to do that. So that's just an aside. The degree of p at x is greater than the degree of q at x by 1, so we're going to have an oblique asymptote. Therefore, we're going to have an oblique asymptote, and we have to divide to find it. So you can do, first of all, look at what we're going to do. We're going to set this up. We have to rearrange things because we have to put them in order. So that's negative x plus 2. And our dividend is going to be x squared. And we're missing, we need a placeholder here, plus 0x plus 1. So if you're doing synthetic division, be very careful with how you set it up. Make sure you set it up correctly. Dividing the first term into the first term is a negative x. Multiply that down, negative x squared, sorry, x squared minus 2x. I'm trying to write really small here, so don't crowd into the next example. Subtract everything here. These are gone. We have a 2x. Bring down the 1. Divide again. Minus 2. Negative 2x minus 4. And that's positive. Did that twice. Positive 2x minus 4. Subtract. These are gone. And this is left with a remainder of 5, which is no problem. I don't really care about that. This is what I care about. This is my oblique asymptote. So I'm going to put that over under the key characteristics. We have an oblique asymptote at y equals negative x minus 2. So now we have to draw that one in. So to review with you how to draw oblique asymptotes, you start with the y-intercept, your b value here. Your b is the y-intercept. That's a negative 2. So I'm going to put a negative 2 on my graph, which is pretty hard to do actually. 2, 4, 6, 8. I'm not even counting by 2 1/4. So maybe here is 2. So put a dot on for your y-intercept roughly. Then we graph our slope. Slope is the m. M is the slope, and our slope is a negative 1. That means when you're talking about rise over run, we have a negative 1 over 1. So I'm going to drop 1 and run 1 from my blue dot. So the blue dot that I just put on for my y-intercept, I'm going to try and drop 1 and run 1, which is pretty hard to do with the scale I have here. And then I'm going to draw a line in between those dots. Okay, well that's the best I can do with my technology here. So please use a ruler and draw in your oblique asymptote there. What about y-intercept? You can tell by looking at the graph, sorry, x-intercept. You can tell by looking at the graph there it doesn't seem to be crossing the x-axis at all. And the reason we know that algebraically is when we look at the numerator, we'd be looking for zeros from the numerator. That would give us the x-intercepts. Because this is squared and we're adding, there's nothing I can sub in for x squared when I add to it that one to it that I'm ever going to get 0. So that we have no x-intercepts. Y-intercept, so we have no x-intercept. Y-intercept, of course, that's our subbing in f at 0, and that gives us 1 over 2 for our y-intercept. So there's all the information that we get from the equation that matches with the graph. Next example, this is a crazy shape here, this one. So it's pretty hard to look at the graph to get a lot of information. It looks like we might have, when I just look at the graph, I could see, you know, it looks like I have an x-intercept and a y-intercept are the same at the origin probably. I probably have a horizontal asymptote here. Remember that they can be crossed. This is the first time today we've seen it crossed. So this one would be crossed. The horizontal asymptotes are for the end behavior. So it definitely looks like this graph is going to be approaching a horizontal asymptote here and here along the x-axis. So let's just get some more information from that. The turning points, we're going to get that information from calculus. So starting with the denominator, restrictions on the denominator. What can x not equal? So we can't factor anything here. Nothing cancels. Let's look at restrictions. X cannot equal what? X cannot equal what? Nothing. And if you want to do that algebraically, what you're doing is you're saying x squared plus 1, when will that equal 0? Bring the 1 over. When will x squared equal negative 1? That's not going to happen. So we have no vertical asymptotes for this one here. no vertical asymptotes because there's no restrictions on the denominator. The denominator, x can be any real number for our denominator. We couldn't factor, we couldn't cancel, there were no holes, or nothing canceled, so there were no holes. What about a x-intercept? X-intercept, remember, comes from the numerator. So that, and you can see it from the graph there, 0, 0 is our x-intercept. That comes from the numerator, and we can also get the y, it's going to be the same number, right? 0. F at 0, 0 is the y-intercept. We get that from the equation 2. What else have we got? Let's look at the degrees. The degree of the numerator, the degree of p at x, that's the numerator, is 1. The degree of q at x, that's the denominator, is 2. So the degree of the numerator is less than the degree of the denominator. So we can't divide, there's no division in this case here. That means we have a horizontal asymptote at y equals 0 when we have this situation here. And this is one we're very comfortable with, right? If I reminded you, your parent function here, degree of the numerator is less than the degree of the denominator. We have a horizontal asymptote at y equals 0. So, and this one is getting crossed, but it gets crossed right here, but we're looking at the end behavior. Our horizontal asymptote is helping us see what's happening at the ends of our function, if there truly are any ends. In general, so here's a summary for you for all those asymptotes. Set the denominator to q at x. We're going to call the denominator q at x. And if you set it equal to 0, so this is the restrictions. We're talking about the restrictions on the denominator. The first thing you do, and we've done this first in pretty much all of our examples, we've looked for restrictions. The restrictions, or the zeros of the denominator, are the vertical asymptotes. Anything else that is not a restriction is in the domain, so any other number is fine. Now we look at the degrees of the numerator, which is p at x, and the denominator. If the degrees are the same, then we do that leading coefficient divided by leading coefficient thing, if the degrees are the same. If the denominator's degree is greater, then you're going to have a horizontal asymptote at y equals 0. That's our typical 1 over x. 1 over x is your base example of that. Your denominator degree is greater. You have that easy horizontal asymptote at the x-axis. This is the hardest one. The numerator's degree is greater by 1, then you have a slant asymptote, which you find by doing long division, and you'll have horizontal or slant, not both. So what I'd like you to do here is press pause, try to do this whole question by yourself with everything you've learned, and then when you come back, I will go over it with you. Okay, did you do it? Did you? I hope so. I hope you'll put some work into this. You're not just waiting for me to keep talking, but you actually tried the question so we could go through it together. If you haven't, do it now. Hurry up, press pause, do it now, because I'm going to go on. First of all, let's look at the degree. The degree, since the degree of p at x, that's a numerator, equals the degree of the denominator, right? We have power of 2, power of 2. This is going to have a horizontal asymptote, and it's not going to be y equals 0. And it's not a slant asymptote. So this degree is equal to this degree. What do you do when the degrees are equal to each other? So it's not an oblique. It's not the easy one straight through the x-axis. Remember, you take the p at x leading coefficient divided by the q at x leading coefficient. So in this case, we've got a horizontal asymptote at 1/4. Hopefully everybody got that. If you did, give yourself a pat on the back. That's the main focus of today, is looking for these asymptotes. So for the vertical asymptote, we need to look for zeros or restrictions of the denominator. Will it factor? Yes, the denominator factors. It's a nice difference of squares. Once you factor it, you can find the vertical asymptote. X cannot equal 3 over 2, that's from this bracket, and negative 3 over 2 from this bracket. So that means we have two vertical asymptotes, one at positive 3/2 and one at negative 3/2. Now to find the zeros or the x-intercepts, they come from the numerator. This does not factor, so you're going to need to use a quadratic formula. Now the question said state all asymptotes and the domain. So the zeros and the intercepts aren't part of that. So even though it's a key characteristic we talked about a lot today, so I wanted to mention it, but we don't need that for this information, for this question, sorry. So here's the domain. We've got a horizontal vertical asymptotes, and the domain is x is an element of real numbers such that x cannot equal 3/2 or negative 3/2. So that's the whole domain. That's what the question is asking. I would encourage you to type this into Desmos or into any graphing software and see what it looks like, because I don't think we did any today with two vertical asymptotes. So you might be interested to see what this would look like. So that is a lot of information today. Do lots of practice. Try to get as many key characteristics as you can down pat. Don't worry about turning points. Just try to get, if you're asked to graph, just put those intercepts on there, put the asymptotes on there, and then kind of fill in the space in between. Good luck.